So here I'm going to discuss nuclear reactions and radioactivity. So the nucleus of an atom can undergo reactions in which the nucleus decays. Now this can happen naturally in the environment or it can be induced in a lab. And there are three types of nuclear decay. There's the alpha decay, beta decay, and gamma decay. So alpha decay specifically is when we have a large nucleus and it wants to become more stable, and so it emits an alpha particle. An alpha particle is a helium atom that has a mass of 4. So here you can see the alpha particle written in nuclear notation. And so if the nucleus of the original atom is going to lose protons, it actually becomes a new element. So here is actually the chemical equation for this alpha decay. So we start with plutonium, and it has a mass of 240, and plutonium has an atomic number of 94. And if it emits an alpha particle, then there's only going to be 92 remaining protons, which is why it's uranium, and its mass is 236. Notice that we have conservation of mass on the left-hand side and on the right-hand side. So if you see here, an alpha decay reaction can be easily spotted because of this helium alpha particle being present on the product side of the chemical equation. Now in beta decay, neutrons actually change into protons, or protons change into neutrons. And there's two different types of beta decay. There's beta minus and beta plus decay. If you take AP Physics or AP Chemistry, we'll go into more detail about those. But what's important to note is that, again, we're actually changing what we are, because you're going from a neutron to a proton or a proton to a neutron. You are changing your number of protons, so you're becoming a different element. Down here shows an example of beta minus decay. So we start with carbon 14, and carbon 14 has 6 protons, and it has 8 neutrons, and a total mass of 14. One of those neutrons becomes a proton. So now instead of 6 protons, you have 7 protons, so you are now nitrogen. Now if you notice, the overall mass does not change because the proton and the neutron have the same mass. So here is the chemical equation for beta minus decay. And on the right hand side you see these other symbols. Actually there's something called an antineutrino that's produced, as well as an electron is emitted from the nucleus of an atom during beta decay. And this is to conserve the charge. So if you go from being neutral to being positively charged, then somehow you had to get rid of something negative. So that's an electron that's produced in the nucleus, right? Now the last kind is gamma decay. And gamma decay is really just when the arrangement of the protons and the neutrons in the nucleus change their shape or their configuration to a lower energy state. So how they're sort of situated in there, they have a specific amount of energy because of their orientation to one another. So if that orientation changes, then they emit a huge amount of energy called a gamma ray. So you can see we're not really changing what the element is, we're just releasing energy because of the change in shape of the nucleus. So again, you can spot these three: the alpha decay by noticing the alpha particle, the beta decay by recognizing the electron that's formed, and then the gamma decay by looking at the energy, or this gamma here that's showing the energy as this type of reaction happens. Now, alpha decay and beta decay and gamma decay have a different power of radiation. Alpha decay is very small and it cannot penetrate the skin. Beta decay can pass into the skin and the tissues. Gamma radiation is the strongest kind of radiation, and it can pass through your tissues and it can pass through concrete. Now, not only can this be generated in a lab, but it can also happen naturally in the environment. And when it happens naturally in the environment, we call it radioactive decay. And it takes a certain amount of time for a nucleus in the environment to do this, and the time is called a half-life. So a half-life is defined by the amount of time it takes half the nuclei in a sample to radioactively decay. So let's say we have thallium-208 and it decays into lead-208. And it has a half-life of 3 minutes and 5 seconds. So that means if we started with 20 atoms and we allowed 3 minutes roughly to go by, now we would have 10 atoms that are thallium and 10 atoms that are lead. So half of the nuclei in here have decayed. Now if we now allow another 3 minutes to pass, another half will have decayed. So 5 more will have changed into lead, and we would only have 5 remaining thallium atoms. So that's what half-life means. Now we use radioactive decay and natural radioactive decay in order to age samples. So this is what carbon dating is. Carbon naturally occurs in 3 different isotopes: carbon 12, 13, and 14, and carbon 14 is actually radioactive. It behaves exactly like carbon 12 chemically, but it is radioactive and will decay over time. So by looking at the number of samples, or the number of carbon 14 atoms we have versus the number of nitrogen 14 atoms you have in a sample, so this is undergoing beta decay, we can then use the half-life of that carbon 14 to determine how old some organism or some fossil sample that we have discovered is. But there is a limitation to carbon dating. We can really only use it up to 50,000 years. All right, so just to give an example of this, it says that we have the half-life of carbon 14 is 5,730 years. If you have a 100-gram sample, how much of carbon 14 would be left after 11,460 years? So in the first 5,730 years, you're going to cut it in half. So you would have only 50 grams of the sample. And then if we allowed another 5,730 years to pass, we would have half of that, so we would have 25 grams. So just make sure that you understand the basics of half-life calculations and the ideas behind the different types of nuclear radiation and nuclear decay.